So, what's the topic for today?
Today's topic is intermolecular forces.
Okay, I've got some ideas about intermolecular forces. So, how about I just launch in and you chime in if something seems, if I make a big mistake, which we know is possible, or if something pops into your head that seems pertinent. Okay, so. Intermolecular forces. Intermolecular forces. Okay. Inter, by the way, means between molecules. So these are forces that hold one molecule near an adjacent molecule. It's not the thing that holds the internal molecule together. It's the intermolecular forces. So, and a few days ago, I took you into the kitchen and I took the muffin tray and we put a bunch of compounds in the muffin containers, and so there's a good chance this video gets placed just after that one. But that was evidence of intermolecular forces, and they're one of the easiest ways for us to find them, or for you and I to see them, are when we look at boiling points and melting points. And that's what I tried to show in the kitchen in that particular day. And we had a number of different compounds that we saw. Some were already gases when I started, some were liquids, some were solids, and then as we let the heat interact with them, some of them started to melt and some of them started to boil. And we can explain those relative melting points and boiling points based on the intermolecular forces that we see in compounds. And so I just want to remind you of some of the different compounds that we saw on that day. For instance, I had some sodium chloride, and I think I had some baking soda, sodium bicarbonate, sodium hydrogen carbonate. We filled up, or the container was actually already filled with some oxygen and some nitrogen. I think I put some water in one of the containers, and there were some oils, like the gasoline that I had, and that was like an octane, so C8H18, and I think I had some other like olive oil and that sort of thing. So those might have been like C20H22 or something like that. I mean, there was just a number of different compounds, and we saw them that day as some of them were gases already, some of them were liquids, some of them were more liquidy than others, I guess, and we had some solids. And so we're going to explain those observations in terms of intermolecular forces. Okay?
Sounds good.
Cool. So I'm going to start off, and I'm going to start with listing those intermolecular forces. And I'm going to list them from strongest to weakest. Okay, and I'm going to give them a name, and then I'm going to tell you what kinds of compounds have them. Is that still on screen?
Yep.
Okay, so that's what we're going to do. All right, so the strongest ones are ionic forces. And ionic forces, funnily enough, are in compounds that are ionic compounds. And we get those, and we saw those, right? We saw those with the sodium chloride and the sodium bicarbonate. those are ionic compounds. Sodium with a plus ion, chloride with a minus ion, with a minus charge, sodium with a plus charge, hydrogen carbonate with a minus charge. So ionic compounds like sodium chloride or sodium hydroxide or potassium iodide, things that have positively charged ions and negatively charged ions, have ionic forces in them. And although we don't often think about sodium chloride and sodium hydroxide and these compounds as being molecular, they certainly have an ionic intermolecular force. And that force comes from this chloride here being attracted to an adjacent sodium. And so this force of attraction across here from one positive ion to a negative ion to this positive ion, wrong color, to a negative ion to a positive ion. All these attractions across here would be ionic bonds or ionic forces, and they are super, super strong. I know they're super strong. I think you know they're super strong as well. Why do you know they're super strong? Because when I put them on the stove and put heat to them, they didn't change at all, right? I mean, they were solids when we started off. We heated them like crazy for 10 or 15 minutes. Nothing happened. So that tells us that the sodium chloride or the sodium bicarbonate or the sodium hydroxide or the potassium iodide, those ionic compounds have super strong bonds holding them together. And so that's one way of thinking about the strongest intermolecular forces as being these ionic forces.
Okay, so the strongest ion is ionic. All right.
Yeah. Does that work for you?
Sounds good.
Okay. Now, I wanted, if you're content with that one, it's pretty easy to see, I think, that ionic compounds have ionic forces, and we've experienced them as being pretty strong. So that's pretty basic, a pretty simple one to understand. I want to jump from the strongest now to the one that is actually the weakest. Okay, so this is the weakest of them.
All right.
So the weakest intermolecular force goes by a couple of different names, but you might sometimes see them called induced dipole forces, or you might see them as London dispersion forces. And sometimes this weakest force and the next weakest are included in a name called van der Waals forces. But they are very weak forces, and they're weak, and I'll explain where they come from after I mention where we'll find them. Every molecule and atom has these forces. Okay, and these weak forces, they come from, well, if they in an atom, if I have a nucleus and I've got a bunch of electrons around the outside, something like this, and I've got some other atom, some other element, same nucleus, same set of electrons that are, and these two atoms, these two elements, these two molecules can come near each other. At any particular time, the atoms might, or the electrons might be in this location. But they might also, at some other time, we might have an unbalance. We might have more electrons over on this side. And so over on this side, we might have a slightly negative region where we've got a few more electrons over here than we do over on this side. At the moment that happens, oh, now we've got a slight positive side to this molecule over here. And so as this neutral element or this neutral compound is just existing, living its merry life the way it wants to live it, there will come times when there are parts of the molecule are slightly negatively charged and some parts of the molecule are slightly positively charged. Oh, and as soon as we have something that's positive over here, now in this adjacent molecule, this has a whole lot of electrons. And those electrons can be attracted, oh, I want to go to my pencil, my color. They can be attracted to this positive side of this molecule, of this element. And so, and now, oh, now the electrons over here are being drawn in this direction. So now this side of this molecule, or this atom, becomes slightly positively charged. And so in a moment-by-moment basis, instantaneously, we can have this force of attraction between these two neutral substances, or these two atoms, or these two molecules that are neutral. And so this force in here is the induced dipole force. It's called dipole because in the atom, or in the element, or in the molecule, there's a slightly positive and a slightly negative part that can occur for just a moment, or an instantaneous moment, for a very short period of time. And so that's the dipole, and they're induced because the molecule doesn't have it all the time, or the atom or the element doesn't have it all the time, it just has it for a few seconds. And it allows, well, way less than a second, but overall for a super short time. But overall, that allows these molecules to be attracted to each other a little bit. But they're super, super weak. So every molecule atom has these weakest forces. They're called dipole forces because at an instantaneous time, and for a very short instantaneous period of time, they will have a slightly positive and a slightly negative part to an atom or a molecule. And that will, this positive side would be attracted to these electrons. Ooh, these electrons are kind of drawn over. Now all of a sudden, this species over here has a slightly negative and a slightly positive end. And now all of a sudden, we've got these two species, these two atoms, these two elements, these two molecules can be drawn to each other. What do you think of that, Kevin?
Yeah, that's great. It's because we know that electrons randomly move and that they're always moving around the nucleus of an atom, that these forces happen in every atom and in every molecule.
Exactly, yeah. Electrons are moving, and because they're moving, sometimes they move to a position that's a little more favorable. So over here, I started off by saying this is a neutral atom or a neutral molecule. The electrons, left to its own devices, everything would be evenly distributed, but the electrons are moving. And so at some point, there's a slight imbalance, and a few more might end up over here on the right-hand side. That makes this right-hand side slightly negatively charged. It means that the left-hand side must be slightly positively charged. And now all of a sudden, we've got a slight positive side over here. And these electrons in an adjacent molecule are attracted to that slight positive charge. And that brings these two species closer together. So it's an intermolecular force. It's a force between these two atoms, between these two molecules, that comes from these electrons being drawn to this temporary induced dipole of this species, of this molecule, of this atom. Okay?
All right, yeah.
Now, these are the weakest ones. So if we go back to my list a few seconds ago, here are the things that we looked at in my kitchen. Sodium chloride, already a solid, right? Already has really strong forces. Of all of these compounds have London dispersion forces, have induced dipole forces, because they've got atoms with electrons and the electrons are moving. But what we know is some of these species only had the weakest possible forces. The weakest possible forces mean that it will have already boiled. It will already be a liquid. And that's the oxygen and the nitrogen, right? When we started off, these had such weak forces, they were already a gas. They'd already separated. One oxygen molecule was already well separated from another oxygen molecule. One nitrogen molecule was already well separated from another nitrogen molecule. And so the forces of attraction holding things that you and I experience as gases together must be very, very weak. And so the weakest of the forces that we see, these induced dipole forces, these London dispersion forces, that's what we would see in something like an oxygen or nitrogen or other things that are gases that become gases very, very easily. They become gases at temperatures lower than you and I experience regularly. Okay?
All right.
So that's the weakest of those forces. The next strongest force after this one, I'm going to write it above it, that's why I left this blank here, are called dipole-dipole forces. And dipole-dipole forces are really nothing more than a permanent case of what we saw down here. Here with the induced dipole forces, they happen occasionally, instantaneously. But with dipole-dipole forces, there's something going on with the molecule such that we've got some atom attached to some other atom, XL, neither of those exist, but this molecule, one end of it is always slightly negative, and one end of it is always slightly positive. And because it always has this slightly negative and this slightly positive end, some other molecule of the same compound also is slightly positive and slightly negative. And so this positive end here is attracted to this negative end here. And so we have some force of attraction between those two. And this force of attraction between these permanent dipole polar molecules is called a dipole-dipole force. And they are a little bit stronger than the weakest possible force. So they're a little stronger, dipole-dipole forces.
All right, so the X or one atom is always positive and the other atom is always negative.
Sort of, except that it's not as positive as sodium and chloride, because in this case, we know that if you have a full 1 plus charge and a full-time 1 minus charge, those where the electron has been transferred from one element to another element. So here we have, a full-time +1, -1, +2, -2 charge. Here, we don't have something that is as permanent as that. This dipole-dipole force, it's permanent, but it's not as strong. So this comes from, you remember, we had a conversation not long ago about electron affinity. Related to electron affinity is a concept called electronegativity. Negativity. And what that says is that inside, electronegativity is a measure of just the desire of when electrons are shared between two atoms, these electrons, in this case, would be slightly more attracted towards the L than they are to the X. And so they spend more of their time, the electrons spend more of their time, these two electrons in this bond spend more of their time down here next to the L. And so that means that this end of this molecule is slightly negatively charged. So electronegativity is a measure of how much an atom wants to borrow electrons or take electrons when they have a chance to be shared. And not too surprisingly, it's very similar to electron affinity in that the elements in the same part of the periodic table want those electrons similarly. And so an electronegative element will draw electrons towards itself in this bond, and as it does that, that means that this end of this molecule becomes slightly negatively charged. It doesn't get the electron full time like the chloride does in sodium chloride. It gets the electron part of the time, more of the time. And so it means that this molecule overall has a slight negative side and a slight positive side, but it has it all the time. And so that slightly negative part can be attracted to the slightly positive part of an adjacent molecule. So if we have electronegativity differences in a shared bond and across the whole molecule, we can have dipole-dipole forces. And so electronegativity differences in a shared bond across the whole molecule, and we can have dipole-dipole forces. And those dipole-dipole forces are a little stronger than the London dispersion forces. What do you think of that, Kevin?
All right, so that's how the dipole-dipole forces work, and they're just like a little bit stronger than the one on the bottom.
Correct.
What type of molecules did we see this with? Or
so you can see it with linear molecules like this that are with linear molecules. So if I have something like a hydrogen chloride or a hydrogen fluoride, or if I have a depending on where we are with Lewis structures and that sort of thing, and figuring out the shapes of molecules. But here we have a hydrogen and a chlorine. We know that chlorine is has a high electron affinity. It has a high electronegativity, and so it will draw electrons down towards the chlorine end, and so this end will be slightly negative. The hydrogen end will be slightly positive. So something like ammonia, which is trigonal pyramidal, you can have each one of these nitrogen-hydrogen bonds, the electrons are drawn up towards the nitrogen. And so this part of the ammonia molecule is slightly negatively charged, and this part of the ammonia molecule is slightly positively charged. And so it will have some attractive forces due to that dipole, that permanent dipole between this ammonia and an adjacent ammonia.
Okay, so it's all based on shape and that electronegativity difference.
Right, yeah. And that goes back to electronegativity is a desire of atoms to attract electrons towards them, just like we saw with electron affinity. Those elements like fluorine, chlorine, oxygen, iodine, those have high electronegativities. They have high electron affinities, and that means that they can help induce a permanent dipole in a molecule. And so you can have these slightly stronger forces in them. Okay, so the fourth type of bonding is hydrogen bonding. And it's not as strong as ionic bonding, but it is stronger than induced dipole or dipole-dipole forces. But it occurs when you have a hydrogen attached to some element that is more electronegative than the hydrogen. So here's a hydrogen bonded to an oxygen, or here's a hydrogen bonded to a nitrogen. And this oxygen can be attached to lots of other things. It could be to a hydrogen. It could be to some carbons and a bunch of other things further down this chain. The critical thing is we've got hydrogen and oxygen, and this oxygen has a couple of lone pairs of electrons. Likewise, this hydrogen attached to nitrogen can be attached to a bunch of other things if we want it to be. Doesn't really matter. But we've got hydrogen and a lone pair of electrons on this nitrogen. Now, this is not this is a hydrogen. This line here represents the hydrogen-oxygen bond. This line here represents the hydrogen-nitrogen bond. That's not the hydrogen bonding that we're talking about. We're talking about, this is a very electronegative element. And so these shared electrons here in this hydrogen-oxygen bond are drawn towards this oxygen. And that means that this oxygen is slightly negatively charged and this hydrogen is slightly positively charged. That positive charge there gives us a chance to form another bond with an adjacent molecule. And so here is another molecule of the exact same compound. Here is a slightly negatively charged oxygen. Here's the slightly positively charged hydrogen. But the hydrogen bond is between, in this hydrogen bonding, is between this positive region here and these lone pairs of electrons on an adjacent molecule. These lone pairs of electrons and this slightly positively charged hydrogen. This bond here is the hydrogen bonding we're talking about. And that is not the most strong bond out there, but it's a pretty strong bond. Another example down here. So I've got this lone pair of electrons on this nitrogen. This is slightly positively charged, slightly negatively charged. It means that some other hydrogen attached to some other nitrogen, we can have a slight positive charge here. This lone pair of electrons and this hydrogen are attracted to each other. That's the hydrogen bonding. It's an intermolecular force. Here's one molecule, here's a second molecule. This hydrogen bond is holding these two molecules together. And it's a reasonably strong bond. Here is one molecule. Here is the second molecule. This hydrogen bond is helping to hold these two molecules together. And it comes from a slightly positively charged hydrogen being attracted to lone pairs of electrons on something that is pretty electronegative. So our order of strongest to weakest. Ionic bonding. Hydrogen bonding. dipole dipole forces, and then induced dipole forces. And these ones up here will have high boiling points and melting points because they have the strongest forces, and these will have the lowest boiling points and melting points. Do you have a comment to make there, Kevin?
No, that list looks all nice and dandy. I think these intermolecular forces, we sometimes acronym IMF, intermolecular forces. These IMFs are pretty tricky, but the main thing to remember is that these aren't actual bonds. These are not covalent bonds. You can't draw them out in a Lewis structure, but they're really important to the chemistry and the nature of this course still. So
yeah,
it's good to learn these.
Yeah, we in worrying about intermolecular forces, we're now talking about understanding physical and chemical properties of molecules once the molecules have already been formed through other types of bonding. Yeah.
All right, I think that's all then.
Okay, all right. Thank you very much, Kevin.
Thank you, Dr. Hunter. You led most of it. Have a good one.
Okay. So can you cut out the part where